Okay, so here's the question you were asking me about. Um, I would argue that you've done most of the hard work at this point, and the simplification from here on out is actually going to be a lot easier than the work you've already done. But just to recap, so that we're on the same page, you started off with this first expression that was given to you on MathXL, and the first step that we decided to do was to group two terms inside the argument. So two terms inside of this large grouping symbol and use them for the sum formula or sum identity for tangent function, and then do that a second time, essentially. So in the first step, we're making the claim that the result from these first two tangent inverses is going to represent our alpha angle, and the result from this tangent inverse is going to represent our beta angle. And once you rewrote that result, you got this, essentially you got this expression here in green. And then once again, we've got another sum of tangents, I should say sum of angles inside of a tangent here and here. And so we used that sum identity for tangent again, and that's how you obtained your second result as well. Now, moving forward from here is actually going to utilize the same rule that we got by establishing this number 3 and this number 3 as well. What you've got to keep in mind is that a trig function and its inverses will essentially undo one another. This phrase, or any phrase that looks like this, tangent evaluated at tangent inverse, is almost always going to return this number as a result. The only time that it wouldn't is if we encounter some sort of weird domain restriction or something like that. So the fact that in this component we had tangent of tangent inverse of 3, that turned into the number 3 out here at the end. That was the sum of tangent inverse of 3, and that's where it turned into the number 3 out here. Similarly, down in the denominator, we had the same thing. Tangent of tangent inverse evaluated at 3 turned into the multiplication of 3. Now, when I simplified it by hand, I put that 3 at the end of the group where it was originally, but the option in MathXL looked like this, and they actually had the number 3 written in front of that grouping symbol. So moving forward from here, it looked like where you had stopped on this question was where does this expression simplify to? And with all of these tangents here, it started to get a bit nerve-wracking. Well, the nice thing is again, you've done all the hard work here. The rest is actually quite simple. Here we have tangent of tangent inverse evaluated at 1. So that's going to simplify to the number 1. Here we have tangent of tangent inverse evaluated at 2. So we're going to simplify that group to the number 2. Down below, tangent tangent inverse of 1, and so on. So at the beginning of this problem, it seemed awfully strange that we were going to blow it up into those multiple levels of trig identities, especially those sum identities for tangent. But now, at this point, hopefully you see the benefit in all that. This wild-looking expression, this wild-looking equation actually simplifies to this. And I would say, well, we've got 1 plus 2 over 1 minus 1 times 2, that fraction plus 3, and all of that is on top of the numerator of a larger fraction. And in the denominator, we have 1 minus 3 times the quantity, well, which is the same fraction as above, 1 plus 2 over 1 minus 1 times 2. And from here, we can continue to simplify. Numerator here, of course, is 3. The denominator, well, 1 times 2 is 2. 1 minus 2 is negative 1 plus 3. That's going to make an interesting result. 1 minus 3 times 3 over negative 1. And I say that this is an interesting result because 3 divided by negative 1 is negative 3, and negative 3 plus 3 is 0. So that's going to be, that gives us a precursor as to what this is going to simplify to. But we'll go ahead and finish this out. 1 minus 3 times negative 3. So negative 3 plus 3 is, of course, 0, and negative 3 times negative 3 is positive 9. 1 plus 9 is 10. Now, it doesn't matter what our denominator is as long as it's not 0. If it was 0, we'd have a problem, but since it's some numerical value, we know that 0 divided by 10 is 0 and 0 only. So at this point in the MathXL question, we're asking what does this expression simplify to? I would say that this large, magnificent expression simply turns into the number 0. And I don't have MathXL on this computer with which I'm recording, but I did type in 0 onto MathXL for your question, and it did accept that. So moving on to the next part of the question. So I've just copied the next part of this question. On the interval 0 to 2 pi, for what values of theta does tangent theta equal 0? Now, this is a little bit different than the sample problems I've been recording in my videos this week. This interval starts at 0, ends at 2 pi, but it's inclusive on both ends. This would be like saying this, 0 less than or equal to theta less than or equal to 2 pi. So if we do get a solution that lands on 2 pi, we are going to include it in our result. In all of the examples in the videos this week, that was not included. So to answer this question, I consider a unit circle, and I ask myself, where in this unit circle does y divided by x, since that's what tangent is defined as, when does the y-coordinate divide by the x-coordinate equal 0? Well, that's only going to happen when the y-coordinate is 0. And when the y-coordinate is 0, the x-coordinate has to be 1 or negative 1. So the two positions in which that occurs is here and here. So normally we would say that theta is equal to the angle measure 0 radians and pi radians, but let's not forget that because of this inclusive component of the interval, we actually have to count this angle a second time when we get back to the end. Normally I wouldn't include this, but the instructions did say to include that. So for this part, I would argue that theta is or can be 0, pi, or 2 pi radians. And again, off screen, I just checked that in MathXL. It did accept. And the next part of question B, by the way, this started part B of the problem. All right, and the next part of the question looks something like this. It asks us, what is the interval in which tangent inverse of 1 plus tangent inverse of 2 plus tangent inverse of 3 must lie? And the answers that we select or that we choose are going to be entered into these boxes here. They must be exact answers using pi as needed. And this gets to be an interesting question, and unfortunately, the domain and range of these trig functions wasn't covered much in our class before we went on remote instruction, so it's a bit hard to pick up on these nuances while you're working at home. But let me just start by reminding you of this, that the original tangent function has a domain of negative pi over 2 to positive pi over 2. So that means that when we're dealing with angle measures that are placed into our tangent function, we're only worried about angle measures that exist on essentially this right side of our unit circle. And as we compute results from our tangent function, and when we take our y values and divide them by our x values, the results end up being any number from negative infinity up to positive infinity. And I used the wrong grouping symbols here. I should have used square brackets. And because of this trig function domain and range restriction, then we would go on to say just the opposite about tangent inverse. With tangent inverse, our domain or our inputs can be any number from negative infinity to positive infinity, and our range or the results must be any number between negative pi over 2 and positive pi over 2. Now, to me, this is where it gets real interesting, because if I had a picture of tangent If I had a picture of tangent, it would look something like this, especially if we restrict the domain from negative pi over 2 to positive pi over 2. We're only talking about this one section or one branch of the tangent function. And if I invert that to represent the graph of tangent inverse, it would look something like this, basically a sideways snake, where the highest point on the snake is going to be pi over 2, and the lowest point on the snake is negative pi over 2. And how that relates to what we're talking about here is that each one of these tangent inverses has an input that's a positive number, an input of 1, 2, or 3. Now, without a calculator, I don't know what tangent inverse of this is going to be. I don't know what tangent inverse of 1 is. I don't know the y-coordinate of that position or this position or that position, but it doesn't matter. What I do know is that that result, since these numbers were positive, that result has to be somewhere in between 0 and pi over 2. So for all of tangent inverse, our solutions exist somewhere between negative pi over 2 and positive pi over 2. But in this particular group, for these three numbers, the answer, the result, the y coordinate to those three positions has to be somewhere between 0 and pi over 2. And so what I'm going to think is this. Well, if the result, or the, let's see here, yeah, the result or the interval for tangent inverse of 1, well, that's somewhere between 0 and pi over 2. And I'm going to use the non-inclusive grouping here because I know that the result is not at either end. Tangent of 0 would have given me exactly 0. This input is not at the very start of that group, and 3 is not at the very end of the group. So I'm going to group them this way. The result for this particular component is somewhere between 0 and pi over 2. The result of this group is somewhere between 0 and pi over 2. And the result of this is somewhere between 0 and pi over 2. Now, if I get three answers that land somewhere between 0 and pi over 2, then when I add these groups together, when I add these regions together, I could have a result somewhere very, very close to 0, but not equal to 0, but somewhere very, very close. So maybe I should say something like this. Y must be an element, so that we're really clear that we're not talking about coordinates here. We're talking about ranges or intervals of results. So I'm saying that y could be somewhere, anywhere between 0, that would be on the low end, right? If the result for this group, and this group was close to 0, then when I add those three answers together, my answer is close to 0. And if I had an answer in each of these groups that's somewhere on the high end, close to pi over 2 each time, well, after I add those three together, I get 3 pi over 2. So again, if the solution to this part was close to pi over 2, and this part was close to pi over 2, and this part was close to pi over 2, then the sum of pi over 2 plus pi over 2 plus pi over 2 is 3 pi over 2. And that's our way of saying, we don't know exactly where these solutions are right now, but I do know that those solutions have to exist somewhere between 0 and 3 pi over 2 when you add all three of them together. And I just punched that into MathXL, and I did like that as an answer. And the very last component of this question says, okay, well, now that you know that, then go ahead and tell us, what does tangent inverse of 1 plus tangent inverse of 2 plus tangent inverse of 3 have to equal? And here again, we don't know what each one individually equals. If I did, I would just find each one individually and add them together. But what we do know at this point, based on a couple of recent arguments, is that the sum of these three inverses has to be somewhere between 0 and 3 pi over 2. So I'm thinking of a unit circle again, somewhere between 0 and 3 pi over 2. So the answer has to be somewhere here. We were also saying that our solutions for theta must be either 0, pi, or 2 pi. 0, pi, or 2 pi. But since 2 pi doesn't exist inside of this interval, we can throw out 2 pi. So let me just write these down and cross them off as we discover that they're no good. 2 pi is not on the interval between 0 and 3 pi over 2. So 2 pi is gone. So that makes me think, well, the solution is either going to be 0 or pi, but then we just said here that the sum of these inverses must be greater than 0. It can't be equal to 0, and the reason for that is because none of these inputs for the tangent inverse was 0 itself. The only time the tangent inverse of a ratio would equal 0 degrees or 0 radians is if that ratio was 0 itself, and none of these were. So I know that 0 is tossed out. That's not available for discussion. And so that leaves us with the only option out of the three that we established at the start of Part B is that the sum of these three inverses must be equal to pi. So again, there's a lot of mental gymnastics that has to go on here, and there's a switch between algebra and trigonometry, some geometry thrown in there, and in the back of our mind, we're always considering domain and range of functions as well to help establish this solution. So I know that this video got kind of long-winded there, but hopefully some of my explanations made a little bit more sense or helped you understand the scenario a little bit better. I'm going to check pi as the answer. Well, the instruction said to verify that this is equal to pi, so I'm glad that it is. And I did just type it into the computer. They accepted that, and that indicates the end of this particular question. So if you've got any more questions or concerns for me, please let me know, and I'll try my best to help you out.